So you got to hear not the Canadian expert on alpha-1, but really one of the world-renowned experts in alpha-1. And I am here to show you the difference between Canadian presentation that is polite and accurate and soft-spoken, precise, and now the American presentation, which is loud and drifts off topic and things like that. And so I'm going to, Ken, of course, was talking about his occasional gray hairs, and I get upset when I find a brown one. So I naturally get to talk about history. And there's where the changer is. I'm going to talk about the background in history, some of which Ken has touched on nicely, so I don't have to go into too much detail. And I'm going to also focus on something that Ken alluded to, which is self-management of alpha-1, which is really what I've concentrated most on over the last 10 or 15 years. And that self-management is done by an organization called AlphaNet, which of course we now have in Canada, and I hope that you'll all avail yourself of that if you haven't already. I'll also briefly mention the Clinical Resource Center program of the Alpha-1 Foundation, because what we'd like to do is breed additional expertise in Canada. You've probably found that Alpha-1 experts are few and far between in Canada. We certainly found that in the United States in the past, and we've tried to foment expertise within the medical community by essentially having patients demand that their physicians become more experienced and expert in the diagnosis and management of alpha-1. There'll be time for questions, I hope. And I'll summarize with some future directions. This is my favorite molecule, alpha-1 antitrypsin. I think some people are confused by terminology. They hear, see, read. First of all, alpha-1 antitrypsin, that molecule, is a protein. It's also known as alpha-1 antitrypsin with a Greek letter alpha. AAT in the scientific literature, it's abbreviated often, but you'll also see it referred to as alpha-1 proteinase inhibitor, especially if you're on prolastin and you look on the box and it says alpha-1 proteinase inhibitor, parentheses, human. That is alpha-1 antitrypsin. I've had patients say, well, if I have alpha-1 antitrypsin deficiency, why are you giving me this alpha-1 proteinase inhibitor stuff? I want alpha-1 antitrypsin. That is the same thing. And so sometimes in scientific literature, you'll also see alpha-1 abbreviated as A1PI for that. Then there's the deficiency of alpha-1, which I often refer to when I'm talking to patients as alpha-1, just so that I don't get tongue-tied repeating alpha-1 antitrypsin deficiency over and over. It's usually abbreviated AATD in medical literature. And I also refer to severe deficiency as opposed to just general deficiency. And that's, by severe deficiency, I mean people that have 2 abnormal genes as opposed to a carrier, or what's officially called a heterozygote, people that have 1 normal gene and 1 abnormal gene. Know that alpha-1 antitrypsin is a protein, and it is specifically a glycoprotein, which means it has sugar molecules stuck on it. It is a protease inhibitor. That means it blocks the action of enzymes that chew up proteins. It has anti-inflammatory properties, perhaps the body's main anti-inflammatory protein, and those anti-inflammatory properties are independent of its ability to block these enzymes that chew up proteins. It's made predominantly in the liver, where it's released into the blood from the liver cells and bathes all the tissues of the body. It is not an enzyme, as many CPT codes and codes from government agencies seem to refer to it. It's not a sugar and it's not a carbohydrate. You don't raise your blood sugar if you take alpha-1 antitrypsin. The history I present this mostly to aggrandize the fact that I've been involved in the history for so long. Not in 1963, though, and as Ken told you, that's when the discovery of alpha-1 antitrypsin deficiency took place. It was a serendipitous discovery. In other words, it was sort of just someone saying, oh, look at this gel. The normal individuals have this band, which, as you can see, is, if I can figure out which, is right here. And here are a couple of gels where that band doesn't seem to be present. I wonder what that is and what it does. It turns out that if alpha-1 hadn't been discovered back then, our current marvelous genome-wide association studies and COPD gene studies and things that are looking at the entire genome and trying to figure out what genes are associated with what disease probably would not have found alpha-1 antitrypsin deficiency as being associated with COPD, because it's such a narrow spike of the broad spectrum of COPD that our modern technology and software is not designed to look for that kind of effect in the genome. They're looking for small effects that affect large numbers of people. So we were lucky in that sense that this was identified, and it remains the most important genetic cause of COPD that we have today, although we think there will be other genes like alpha-1 that will eventually be discovered. Naturally, the senior scientist who found that this band was missing called in his student and said, go look at those charts, go talk to those patients, see what these people have in common. Came back, said, oh, there seems to be a lot of emphysema at a young age, and it seems to run in families, and thus the 1963 article that associated a deficiency of this protein, which they named alpha-1 antitrypsin, even though while trypsin is a protease that alpha-1 antitrypsin blocks, alpha-1 antitrypsin essentially never sees trypsin, which is a digestive enzyme made in the pancreas, and which alpha-1 would only see if there happened to be a hole in your intestine. They called it alpha-1 antitrypsin, and they said it was associated with familial emphysema, or as they say in Sweden, familial emphysema. And so independent of that, in the early 60s, a US investigator found that he could cause emphysema in laboratory animals by putting an enzyme called elastase, which Ken talked about, into the lungs of laboratory animals. Put a drop of an elastase. In the case of the first experiments, they used an elastase from the sap of the papaya tree called papain. It's the active ingredient in Adolph's meat tenderizer, if any of you are old enough to remember that. And he put that into their lungs, and they got emphysema. And it turned out that the reason that they got emphysema was that the unique aspect of papain, or a unique aspect of it, is that besides making steaks tender, it destroys elastin, and that's what an elastase is. Maybe that's actually the reason that it makes steaks tender, is because it destroys elastin. And it turned out that there were many elastases that had been identified at that time from bacteria, from pig pancreases, and it turned out it didn't matter where an elastase came from. If you had an enzyme that could chew up elastin, you had an enzyme that could chew up lung tissue and cause emphysema, essentially destroy the air sacs of the lung, which are surrounded by a basket weave of elastin fibers. And when they're chewed up, they fall apart. And that is emphysema. The problem was none of these elastases were elastases that had access to human lungs. Unless you worked in an Adolph's meat tenderizer plant, you don't inhale a lot of elastase. People were smart enough, as Ken mentioned, in 1964, the Surgeon General's report not only associated cigarette smoke with emphysema, it associated cigarette smoke with the development, not only associated with lung cancer, it associated cigarette smoke with the development of COPD and emphysema. They were smart enough to say, well, maybe tobacco leaves have elastase in them, or tobacco smoke. very logical and potential, breakthrough, but it turned out there was no elastase in tobacco smoke or tobacco leaves. So it was thought to be maybe just a lab artifact, an interesting little model, but may not have any basis in the development of human disease. Independently of all this, 1969 was the first description of newborns with ZZ alpha-1 antitrypsin deficiency, or ZZ as some people call it. We're dying of what they called neonatal cirrhosis, liver failure during the first months or years of life. And that was really the first association with liver disease and alpha-1 antitrypsin deficiency, which you'll hear more about in the next presentation. Late 1960s, 1970, an investigator in New York discovered that white blood cells, the primary acute inflammatory white blood cell called a neutrophil, contained a very potent elastase. This is an investigator who was not interested in lung disease. He was a pathologist who was interested in shock, what happens to the body when it goes into shock. One of the things that happens is the white blood cells release their contents, and he was kind of cataloging that. And it was about 1970 that I joined his laboratory to do my PhD, and he essentially said, go find out what this elastase does. And so I went to the literature. I had some tissues he provided with me to see what injury this might cause. I found this strange disease from Sweden that only affects those Swedes. And together, he and I did 3 simple experiments that only took 6 years. The first was we put this neutrophil elastase, this elastase from human white blood cells, into the lungs of rats and showed that it was extremely potent at causing emphysema. Minuscule amounts dropped, on one day into the windpipe of a rat would cause significant emphysema in about a month in these animals. Then we showed that if you take this solution of white blood cell elastase in a test tube and you mix it with some human alpha-1 antitrypsin and put it into those rat lungs, the animals didn't get emphysema. And we went on to show the interaction of alpha-1 antitrypsin and human white blood cell elastase. And then the final thing we did was we took a solution of white blood cell elastase, alpha-1 antitrypsin, and then we took a cigarette and we bubbled some cigarette smoke through that solution and found that if we put that then into rat lungs, the animals got emphysema, and went on to show that there are chemicals in cigarette smoke that destroy the function of alpha-1 antitrypsin as a blocker of this neutrophil elastase. And in 1973, we published the protease pathogenesis model of pulmonary emphysema, in which we said the vast majority, that everyone that gets emphysema gets it because they're alpha-1 antitrypsin deficient. That in the vast majority of people who are born with normal alpha-1, that deficiency is functional due to the action of cigarette smoke on the alpha-1 antitrypsin in the lung. And then there's a small group of Swedes there where the deficiency is genetic, not functional. And we even showed that if you take a healthy medical student and you have them have a bronchoscope put down their windpipe, and you look at the amount of alpha-1 antitrypsin that's active in their lung lining, and then you have that medical student smoke one cigarette, that it destroys the function of all the alpha-1 antitrypsin in a normal, healthy lung. And so basically, every time a smoker smokes a cigarette, they make themselves temporarily severely alpha-1 antitrypsin deficient. And the action that takes place can be perpetuated by simply lighting up that cigarette within the next 30 minutes before the liver can replace all of that alpha-1 in a normal individual. And it also points out the danger to a patient who's genetically deficient in alpha-1 who also smokes cigarettes. The liver disease in adults was noticed in the 1970s, that some people with alpha-1 were getting cirrhosis in their later years. some even requiring liver transplants because of that. And what does getting a liver transplant do? It makes you so you're not alpha-1 antitrypsin deficient anymore. Unless, of course, by mistake, they give you a ZZ liver, which has happened. And so 1980s, as Ken showed you, was the idea that was brought forward in the NIH. Essentially, we know now why alpha-1 antitrypsin deficiency causes emphysema. What can we do to protect patients? And the simple idea that seems obvious now was pretty dramatic at the time. They said, well, why don't we purify alpha-1 antitrypsin protein from the plasma of healthy volunteers and give it to patients that have alpha-1 antitrypsin deficiency and see if we can replenish their protein. And as you also saw in the graph that Ken showed, alpha-1 antitrypsin is cleared fairly dramatically and rapidly from the blood after it's given. And in fact, the same thing happens after it's made. In fact, the liver makes more alpha-1 antitrypsin protein than almost any other protein that it makes because the levels are very high in the plasma, and yet it's cleared very fast. It's kind of like trying to keep a bathtub full when the drain is wide open. You have to open up that faucet dramatically in order to keep that level up when the drain is wide open. And that's what liver making alpha-1 antitrypsin for the blood looks like. That's why it takes weekly infusions of large amount of protein to protect the lung. The first treatment using this was approved in December of 1987 in the United States, and for 15 years we had one drug, kind of as you have now if you have any drug, and that was prolastin. And then after 15 years we started accumulating additional products till now we have 4 augmentation therapy products, all plasma derived, all approved by showing that they were no worse than prolastin in safety and the ability to raise blood levels and lung levels of augmentation therapy. And I will also mention that we assumed in the early days of alpha-1 that the reason that ZZ patients had low levels of alpha-1 antitrypsin in their blood was because something in the gene kept the liver from making enough alpha-1 antitrypsin. A logical assumption that turned out to be entirely wrong. In fact, ZZ individuals' liver cells make normal amounts of alpha-1. The problem is in shipment, not manufacture. And so the alpha-1 that's made, as you'll hear from the liver talk that follows, is trapped in the liver cells, and that's the cause of liver disease, or presumed to be the cause of liver disease. So it's an entirely different mechanism. It's the reason that we don't give augmentation therapy to treat liver disease, because the mechanism of liver disease is distinct from the mechanism of lung disease. So how rare is this really rare genetic condition? Well, there's an article that came out in the 90s that suggested that about 100,000 individuals in the United States have severe alpha-1 antitrypsin deficiency, 2 abnormal genes. And that was a study that was done by testing all the blood in the blood bank of St. Louis, seeing what percentage of those donated blood units had alpha-1 antitrypsin deficiency, and then multiplying that percentage by the population of the United States. If there are about 100,000 people in the country with severe deficiency, we've only identified presently between 5 and 10% of those individuals. Why do the remainder remain undiagnosed, that submerged part of the iceberg? One theory was they're all healthy, because we knew that people could have severe deficiency and never have a sick day in their lives attributable to alpha-1 antitrypsin deficiency, and maybe those are just the 90% of people who happen to be healthy. That was kind of belied by work that was done where we tested individuals who had COPD to see what the prevalence of abnormal genes in the general COPD population was. And the consensus of those trials suggested that about 1% of people with COPD, the general diagnosis of COPD, had alpha-1 antitrypsin deficiency, and obviously the vast majority of them didn't know they have it. And these are fairly large studies. They could be large studies because there are about 15 million people in the United States that are diagnosed with COPD, and an excellent article several years ago showed that there are about 15 million additional people in the US with COPD who have not yet been diagnosed because doctors don't all do spirometry. And so if you take the 30 million people in the US with COPD and you assume that 1% of those have undetected severe alpha-1 antitrypsin deficiency, you get 300,000 individuals with severe COPD and severe alpha-1 antitrypsin deficiency. So how does that jive with the 100,000 total, most of which are healthy? And the fact is, it doesn't jive with that. You have to then say, well, who would be a blood donor in St. Louis? And it's generally going to be a healthy young adult. Probably not someone with severe COPD, probably not someone with liver disease that's of any significance. It's not kids, for certain, who aren't blood donors. And so maybe that 100,000 represents the number of healthy individuals, healthy young adult individuals in the United States with alpha-1. Then there's the 300,000 that have COPD and alpha-1. Then there's that unknown number that have liver disease without COPD and alpha-1. And then there's the number that are kids that have yet to be discovered or have no disease at the present time. So maybe there's as many as 500,000 people in the United States that have alpha-1 antitrypsin deficiency, with less than 1% of them being identified, which is a big problem and the reason that we focus on detection so much. So I don't have to tell you what my son is trying to say here, that the good gene is the M gene, and that the bad gene is the Z gene. And the reason he's wearing his Viking costume is because there's evidence that the patient 0, the first patient to have that mutation, is from the Baltic area, Scandinavia, Latvia, things like that. And that was about 93 generations ago from gene mapping. We know that now. Maybe not a Viking, but a Latvian warrior. And my son is now 23 years old, and I promised him about 20 years ago that I'd never show this slide anymore. So what's the difference between the gene that codes for the M protein, the normal protein, and the gene that codes for the Z protein? See, I'm getting better at saying Z. Well, the total gene that codes for alpha-1 antitrypsin deficiency is about 14,000 base pairs long. You know, that spiraling DNA molecule with these stair steps. Each stair step is a base pair. And the difference between the M gene and the Z gene is a difference of 1 base pair substitution out of those 14,000 base pairs that make up the alpha-1 gene. And that single base pair substitution leads to a single amino acid substitution, so that of the 394 amino acids that make up the string of pearls that is the alpha-1 protein, one of those pearls is a black pearl. And that's all it takes to change a normal M protein to a severely deficient Z protein. But that's a magical pearl, if you will, and causes the protein to misfold, get trapped in the liver, and lead to deficiency. It's a pretty good elastase inhibitor if you can get it out of the liver. And so there's this storage of good stuff in the liver that would be great if you could get it out into the circulation. That would be potential cure for alpha-1 if that could happen easily, safely, and cheaply. Nothing on that yet. So what about those carriers, those heterozygotes? Well, most of you know about dominant and recessive genetics. The dominant gene predominates in a carrier. So if you have 2 brown-eyed genes, you have brown eyes. You have 2 blue-eyed genes, you have blue eyes. You have 1 brown-eyed gene and 1 blue-eyed gene. You have brown eyes because brown gene is dominant and the blue-eyed gene is recessive. Throw that all out the window for alpha-1 because alpha-1 has codominant expression. Each gene expresses itself equally. If an MM individual, normal alpha-1 genotype, has a level that's this high, the left-hand bar, and an MZ individual has, a ZZ individual has a level that's about 10 to 15% of normal, that's the second bar. Someone with one of each genes doesn't have a level that's normal, as it would if M was dominant. They have a level that's intermediate between those two. And a lot of work is about to begin trying to identify what the risk is to that MZ individual. Because there is some evidence that there is some increased risk of lung disease. The risk of liver disease is really unknown. And we want to know, is it that some MZ individuals are at high risk and the rest are at a normal risk, or is there a general slight increased risk in everyone, which would have different implications in terms of treatment and things like that. How do you diagnose alpha-1? You know. You get a tube of blood, or you stick someone's finger, or you go to CSI Miami and get your cheek swabbed. We have all of those things available. The important thing is you can't just do one kind of test. There are 3 kinds of tests you could do. You could do a level of alpha-1 antitrypsin protein in the blood. You could look at the protein in the blood in a gel and see how it migrates in an electric field. That's called pi typing. Or you could do a genotype. Now, you would think in a genetic disease, genotyping would be the gold standard, but a lot depends on how the genotyping is done. Most genotyping only looks for the most common abnormal genes for alpha-1 and assumes if you don't have one of those that you're normal. And so if you have any rare genotypes, you have to go further than those things. But anyway, from the tube of blood, you could get any of those 3. From a finger stick, yellow might be hard to see, you can do any of those things. From the buccal swab, which we don't recommend, you can only do genotyping. And it's always good to do at least 2 kinds of tests to know if you need to look for those rare genotypes. The differences between these various testing things are very difficult for doctors to understand. So you guys need to learn the differences so you can teach your doctor. And alpha-1 antitrypsin deficiency, and this may be the most important sentence that I say in this presentation, is a laboratory diagnosis, not a clinical diagnosis. When I speak to pulmonologists, I'll often say, did you know that the guidelines for alpha-1 say that everyone with COPD should be tested for alpha-1? And the pulmonologists say, I love those guidelines, but I know an alpha-1 patient when I see one. That is a mistake, to put it kindly. You can't tell an alpha-1 patient when you see one. You may suspect if someone is 28 years old and has severe emphysema that person has alpha-1, but for many doctors, that's the only person they will test. And we know that people get identified with alpha-1 in their 70s and 80s and things like that. And so you really do have to test everyone. And really what we want to do is newborn screening eventually, because we can't answer questions like, what's the prevalence of aneurysm in alpha-1, and is that different than the general population, until we have general screening for alpha-1 so we can say, okay, in a population of alpha-1 patients, this is the percentage of people that get aneurysms, and that is 5% higher than the general population. Until we have large numbers, and it's not a selected population, for instance, people with lung disease, and that's why they got tested, we're not going to be able to answer those questions. The most common email I get in my inbox from patients is, I have X and I have alpha-1, are the 2 related? And 9 times out of 10, the answer is, there's no way we could know. Whether X is lupus, or X is leg pain, or X is brown hair, I can't necessarily say whether that's related to their alpha-1 with the information we have right now. And you heard about the testing programs that are available. And we also do, a growing number of labs do gene sequencing to find these people. The lung disease of alpha-1 is emphysema, generally at the base of the lungs. leading to destruction of the air sacs of the lung, the business end of the lung where the oxygen and carbon dioxide is exchanged. You heard a little bit about treatment. People with alpha-1 COPD have an advantage over COPD in general. COPD in general is treated in these ways. Alpha-1 patients get to add one more treatment, and only the treatments in orange are ones that have been demonstrably better at prolonging life. They improve survival. And augmentation therapy is one of those things, and I'm going to show you a little more data about that. The liver disease you'll hear more of. This is the new US clinical practice guideline of alpha-1, one of the only publications in alpha-1 antitrypsin deficiency that doesn't have Ken Chapman's name on it. And that's why we limited it to US. And among the things that this new guideline says is that anyone with severe deficiency of alpha-1 antitrypsin and emphysema should be treated with augmentation therapy, or at least should be considered for treatment with augmentation therapy. It doesn't even, we don't even say that FEV1 should be a measure of when to start and who to start, because FEV1, the ability of air to be exhaled with speed from your lungs, is a measure of airway caliber, airway twitchiness, airway disease. Emphysema is a disease of the air sacs. People can have normal spirometry and terrible emphysema with alpha-1. And if you use the standard guidelines that say people with FEV1s between 30% and 65%, you can have someone on oxygen with a terrible diffusing capacity and CT evidence of emphysema, and some guidelines would say that person can't get augmentation therapy when that's exactly what they need. So that's one of the things the guideline recommends. It also continues to recommend testing and raises the possibility that newborn screening should be considered for alpha-1 antitrypsin deficiency. I'm going to shift gears for the end of the talk and start to talk about all those crazy US organizations and what they do. There has been, over the years, the Alpha-1 Association, the Alpha-1 Advocacy Alliance, the Alpha-1 Foundation, AlphaNet, the Alpha-1 Project, the Alpha Beaters and the Flalfas, and the COPD Foundation. And in every one of the cases, or the majority of them, 3 patients had a hand in doing all those organizations that you see, and those are John Walsh, Susan Stanley, and Sandy Lindsay, all 3 of whom have passed away. I would love to spend an hour talking about John Walsh, who was the most amazing individual really in the world. If you don't know about John Walsh, nothing I could say would be believable to you about the things he accomplished. And if you did know John Walsh, then nothing more needs to be said, because once you've met John Walsh, you know what a force of nature he was. And so everything that I'm going to talk about is thanks to these 3 patients. The Alpha-1 Association and the Alpha-1 Advocacy Alliance are no more. They've been absorbed into the Alpha-1 Foundation, or merged with the Alpha-1 Foundation, as we like to say, and with some of the personnel moving into the foundation. The Alpha-1 Foundation is based in a beautiful building in Coral Gables. It is owned by AlphaNet, and the 2 organizations are on the 2 floors of the building. And so you can see just physically the close association between our organizations. The Alpha-1 Foundation, I'll talk about in a second. The Alpha-1 Project I won't talk about, except to say that it is one of the newest organizations. It is a for-profit subsidiary of the Alpha-1 Foundation that is a venture philanthropy organization. It makes investments in the pharmaceutical and biotech industry to move technology towards treating alpha-1, and in return for its investment, it expects stock, royalties, things like that, to make money to support more research in alpha-1. And the COPD Foundation, which is should be a huge organization, after all representing 30 million people in the United States, initially was the Alpha-1 Foundation doing business as the COPD Foundation, and eventually set itself on its own, and it's doing well. So the Alpha-1 Foundation Remember the year 1995. It was started by those 3 patients that I mentioned. It's a not-for-profit. Its mission, simply, I won't put the whole mission statement, is support research, support detection, and find a cure. And I'm sure Henry will say it much more elegantly when he gets to talk. He'll tell you about this, but it gives out research grants, it funds scientific meetings, it has a registry, much like the Canadian registry, has over 6,000 individuals with alpha-1 in it. It does educational materials in many languages. It has a clinical resource center program, which is a program to encourage expertise in clinicians to be essentially centers of excellence in alpha-1, and it drives detection in the United States. AlphaNet its motto is alpha serving alphas, and you'll see why that is. Its purpose is the provision of health management services to persons affected by alpha-1 and to be a money-making not-for-profit, because every dollar that AlphaNet makes in excess of expenses, it donates to the Alpha-1 Foundation. That's how we can have a big research program. That's how the Alpha-1 Foundation can say, look, donor, every cent of every dollar you give us goes to research because our expenses are covered and then some by AlphaNet. It was formed at the same time as the Alpha-1 Foundation by the same 3 patients. It was initially designed to be a home IV company that would turn its profits over to the foundation. But we quickly enrolled as many patients as we could. Then there was a shortage of Prolastin. The Prolastin Direct program came in, and we managed the Prolastin Direct program. And now that there are 4 drugs in the market, we manage programs for all 4 drugs. We hire alpha-1 patients to be disease management coordinators. You'll hear about that in a second. In December of 2016, we celebrated reaching our $50 millionth of donation to the Alpha-1 Foundation based on this model that was thought up by those 3 patients. So from 1999, when the direct program started, to now, we've actually served over 15,000 patients, but unfortunately, our current number is about 6,500 because as new patients get added, other patients die. Every year we've gained patients net, but every year it's because we've gained more patients than we've lost. So, we all have to remember that there are tables and tables of patients who aren't at this meeting because they didn't survive their alpha-1 antitrypsin deficiency. So we have a long way to go. We enroll and educate patients. We we monitor infusion supplies, and we order infusion supplies for our patients. We do nursing quality and training. We have the Alpha-1 Disease Management and Prevention Health Management Program, which is a patient self-management program. We do physician consultations. We do physician, nurse, and respiratory therapist certification and continuing education. We follow this all with patient satisfaction surveys, and we give caregiver support as well, and we provide feedback to the companies about where they could improve their services. This ADMAP program, this disease management and prevention program, this self-management program was rolled out in 2003. We did an outcome study to see how patients were doing before and after the disease management program and showed that we improved. They had fewer hospitalizations, fewer ER visits, less use of antibiotics, less use of steroids, more accurate use of antibiotics and steroids. And so it's been a remarkable success. It's all based on the BFRG, the Big Fat Reference Guide to Alpha-1, and our 13 skinny little reference guides, which are back in the back corner, and which are in many languages, and which are 13 little reference guides that are the highest hit rates of visits to the website, the most interesting topics to patients that we've kind of condensed and modernized. We have about 60 full-time AlphaNet coordinators, all of whom are Alpha-1 patients. They contact more than 6,000 alphas at least monthly by telephone. They work from their homes, they're regionally based, and their job is to help patients manage themselves better. We have more than 200 AlphaNet Canada subscribers who are currently followed by 2 AlphaNet coordinators. They are both Alpha-1 patients, as is the manager of AlphaNet Canada, who's in the back of the room on the right. And one of our coordinators is here, although he's a leaving coordinator, unfortunately. He is, our coordinators graduate into bigger and better things as time goes by. We've learned that happens. The medical team is able to contact subscribers' physicians and other healthcare professionals if patients want. We have exceptionally high subscriber satisfaction rates when we do surveys, and we have proven research, clinical research capabilities. We've done 3 IRB-approved studies within AlphaNet that we sponsored ourselves, as well as acting as a contract research organization for virtually every study done in the United States. And the key element of AlphaNet is its comprehensive health self-management program, and Ken already went over the benefits of good self-management. We follow in the US over 85% of all patients currently receiving augmentation therapy in the US, regardless of drug. The Big Fat Reference Guide is now available not only in print, but online on its own website, bfrg.org, on thumb drives, on an app available for Apple systems, and pretty soon on Android apps. And we also do our nurse education and our physician education, things like that. We take care of the patient's medication list. We look at healthcare utilization with questionnaires we give our patients, health-related quality of life measures. Exercise, diet, and weight control is a separate entity that we have done under it. About 500 of our Alpha-1 patients have home high-end spirometers, and they do spirometry every 6 months. We're just preparing a paper for publication. The average number of spirometry readings we have per patient is about 700 over the course of the years AlphaNet has been in business. Among those 500 people with spirometers, I can tell you the range of the number of spirometry measurements we have on those 500 patients. We have patients who've only done 2, and we have patients that have done close to 900 spirometry readings over the course of the years they've had their spirometry. We also have data that we collect on our patients. Currently, they have completed 466,000 or so questionnaires every month. They don't complete 400,000 every month. They've completed monthly questionnaires that total that. We have over nearly 14 million data points that we are analyzing as I speak, and another 1 million data points from the patients that we've lost that we can compare to those who survived. And how do we look at survival? I'm just going to end by talking a little bit about survival. This is called the Kaplan-Meier Curve. The x-axis is the age of the person when they died. The y-axis is what % of people died at that particular age. And one of the things that we tend to talk about in scientific literature is the median survival. That's the age at which half the patients with a given condition or a given abnormality are alive and half are dead. It doesn't mean that when we say the median survival is 49 years of age, it doesn't mean give up at 49 because I'm a goner. It means that that's the median point for it, and it's a way of looking at the survival with a disease. For instance, in this case, the 50% survival line is that horizontal line where it hits the curve. You just drop it down, and you can see that this group of people has a median survival that's in the 72, 73 years of age range. This is the survival curve for all of our AlphaNet participants. This is important because the one study that was done before the institution of disease management, before the availability of augmentation therapy, was a Danish study which said that of alpha-1 antitrypsin deficient patients with lung disease, the median survival was 49 years of age. This is different than 49 years of age. We actually divide our patients up by those who have been practicing disease management at different numbers for different numbers of years. And in fact, the longer someone participates in the disease management program, and accounting for people who die while they're in that, the longer someone will live. The green curve on the far right is the curve of survival of patients who've been doing disease management for a number of years. And you can see there's actually only barely reaches the 50% line. And in fact, if you summarize the data, and this is really a gross summarization, I can't put error bars on this or scientific things like that. There's the Danish study from 1994, which said that the median survival of a patient with alpha-1 antitrypsin deficiency and lung disease was 49.4 years of age. In 2003, before we rolled out disease management, the AlphaNet median survival was 60.3 years of age. All those people are on augmentation therapy. That's the main distinguishing feature between the Danish group and the group in 2003 in AlphaNet. Then we rolled out disease management, and our latest survival numbers for AlphaNet in the group on augmentation therapy and disease management is 80.4 years of age. So while it's a gross estimate, it looks as if there's a contribution both of augmentation therapy and education of patients in self-management that contribute to longer life. There were other things that happened during this time. We got long-acting, bronchodilators and things along those lines that look like they might have a signal pointing to longer survival in COPD. And so that may be contributing to this beneficial trend in survival in alpha-1. So in summary, AlphaNet's the only patient-centered care provider returning significant funds to research. The quality of its care and management are recognized by patients in the scientific community. We've done over 31 publications in peer-reviewed journals about our disease management program and its effectiveness. AlphaNet's health management program is unique, comprehensive, and already having a dramatic effect on improving patient healthcare utilization and quality of life. And AlphaNet Canada is available to you all if you have alpha-1 antitrypsin deficiency, and it costs you nothing. AlphaNet was founded by alpha-1 patients. It's governed by alphas. The bylaws of AlphaNet say that over 50% of the board of the organization has to be patients affected by alpha-1. It employs alpha-1 patients. It provides services to alpha-1, and it funds research for alphas. It is alpha serving alphas. Thank you.